Welcome. Today, we're exploring the inner workings of HashMap in Java. HashMap is one of the most widely used data structures in the Java collections framework, offering efficient storage and retrieval of key-value pairs. Understanding how it works is crucial, especially before diving into more advanced topics like thread-safe collections. We'll break down the core concepts, see how data is stored, and uncover the mechanisms that make HashMap both powerful and efficient. Let's start by understanding why HashMap is so essential in Java programming and what makes it stand out among other collections. HashMap isn't just another collection, it's a foundation for many Java applications. Its design allows for fast access to data, making it ideal for scenarios where quick lookups are necessary. Before we can appreciate more advanced collections like ConcurrentHashMap, it's important to grasp how HashMap operates internally. This understanding will help you write more efficient, reliable code and troubleshoot issues more effectively. So let's dig into the basic theory and see what makes HashMap tick. At its core, a HashMap stores data in key-value pairs. Each key is unique, and each value is associated with a specific key. When you want to store or retrieve data, you use the key to access the corresponding value. This direct access is what makes HashMap so efficient compared to lists or arrays, where you might need to search through elements one by one. But how does HashMap achieve this speed? The answer lies in hashing and buckets. Hashing is a process where a function takes an input, like a key, and transforms it into a fixed-length value called a hash. This hash is then used to determine where the value should be stored in the HashMap. The beauty of hashing is that it allows for quick calculations and efficient data placement. However, it's important to note that you can't reverse a hash to get the original input. It's a one-way function. This is the first step in how HashMap organizes its data. Once a key is hashed, the resulting value is used to determine which bucket will store the key-value pair. Think of buckets as containers within the HashMap. Each bucket can hold one or more entries. The number of buckets is determined by the HashMap's capacity, and the hash value helps decide which bucket to use. This system allows HashMap to quickly locate where a value should go or where it can be found later. In HashMap, each entry consists of a key and a value. The key is used to generate a hash, which then determines the bucket for storage. Values are what you retrieve when you provide the correct key. This association between keys and values is what makes HashMap so flexible. You can use any object as a key, not just numbers or strings. This flexibility is a major advantage over arrays, which use only integer indices. Sometimes two different keys can produce the same hash value. When this happens, both entries are directed to the same bucket. This situation is called a collision. Collisions are a natural part of hashing, and HashMap has strategies to handle them efficiently. Without proper collision handling, data could be lost or overwritten, so it's a critical part of the HashMap design. HashMap uses a technique called separate chaining to resolve collisions. When two entries land in the same bucket, they are stored in a collection within that bucket. By default, this collection is a linked list. This way, multiple key-value pairs can coexist in the same bucket without overwriting each other. Java also supports another method called open addressing, but HashMap sticks with separate chaining for its implementation. When you add a key-value pair to a HashMap using the put method, the key is first hashed. The hash value is then used to select the appropriate bucket. If the bucket is empty, the entry is simply added. If not, HashMap checks for collisions. If another entry with the same key exists, its value is updated. Otherwise, the new entry is added to the bucket's collection, handling any collisions gracefully. HashMap offers several advantages over other data structures like lists or arrays. First, it provides direct access to values without needing to iterate through all elements. Second, the speed of access doesn't depend on the number of elements, making it highly efficient. Third, HashMap supports dynamic resizing, so you don't have to worry about running out of space. Finally, it allows any object type as a key, not just integers. One of the key strengths of HashMap is its performance. In the average case, both put and get operations have a constant time complexity, O1. This means that no matter how many elements are in the map, accessing a value by its key is fast. This efficiency is a major reason why HashMap is so popular for storing and retrieving data in Java. There are two main techniques for handling collisions in HashMaps: separate chaining and open addressing. Java's HashMap uses separate chaining, where each bucket contains a collection of entries. Open addressing, on the other hand, tries to find another empty bucket for the new entry. While both methods have their pros and cons, separate chaining is preferred in Java for its simplicity and effectiveness. With separate chaining, each bucket in the HashMap can hold multiple key-value pairs. When a collision occurs, the new entry is simply added to the collection within the bucket. This approach ensures that all entries are preserved, even when their keys produce the same hash value. It's a straightforward and reliable way to handle collisions. When you want to retrieve a value from a hash map, you use the get method with the key. The key is hashed, and the hash value points to the correct bucket. If the bucket contains multiple entries due to collisions, HashMap iterates through them to find the matching key. Once found, it returns the associated value. This process is usually very fast, but can take longer if many collisions occur. Each bucket in a hash map is essentially a collection of key-value pairs. In Java, this collection is typically a linked list. When a collision occurs, new entries are simply added to the end of the list. This design keeps the hash map efficient and easy to manage, even as more entries are added. By default, each bucket in a hash map is implemented as a linked list. This means that when multiple entries share the same bucket, they are linked together in a sequence. The hash map can quickly traverse this list to find the correct entry. This approach works well for most cases, but can become less efficient if too many entries end up in the same bucket. Starting with Java 8, HashMap introduces an optimization called treeification. When a bucket contains too many entries, specifically 8 or more, the collection is converted from a linked list to a red-black tree. This change improves performance, reducing the time complexity for operations in that bucket from O(n) to O log n. Treeification only happens if the total number of buckets is at least 64. Treeification is triggered when two conditions are met. The number of entries in a bucket reaches 8 or more, and the total number of buckets is at least 64. This ensures that treeification only occurs when it's truly beneficial for performance. If these conditions aren't met, the bucket remains a linked list, which is sufficient for smaller collections. A red-black tree is a self-balancing binary search tree. When a bucket is treeified, entries are organized in this structure, allowing for faster searches, insertions, and deletions. The time complexity for these operations becomes O log n, which is much better than the O(n) of a linked list when many entries are present. Each entry in a hash map is represented by a node object. This node contains the hash value, the key, the value, and a reference to the next node in the bucket. This structure allows HashMap to efficiently link entries together within a bucket, whether it's a linked list or a red-black tree. One of the great features of HashMap is dynamic resizing. As you add more entries, HashMap automatically increases the number of buckets to maintain performance. This resizing ensures that the average time complexity for put and get operations remains close to O(1), even as the map grows. When you create a hash map, you can specify the initial capacity number of buckets and the load factor, the threshold for resizing. By default, HashMap starts with 16 buckets and a load factor of 0.75. This means resizing happens when the map is 75% full, balancing memory usage and performance. Resizing happens when the number of entries exceeds the product of the load factor and the current capacity. For example, with 16 buckets and a load factor of 0.75, resizing occurs after 12 entries. When resizing, the number of buckets doubles and all existing entries are rehashed and redistributed. When HashMap resizes, it needs to rehash all existing entries. This means recalculating the bucket index for each entry based on the new capacity. This process ensures that entries are evenly distributed across the new set of buckets, maintaining efficient access times. In Java's HashMap, the index for a bucket isn't calculated using the modulo operator. Instead, a bitwise AND operation is used, hash and capacity 1. This optimization is faster than modulo and works because the capacity is always a power of 2. It's a subtle but important detail that boosts performance. Let's look at an example. If the hash is 37 and the capacity is 16, the index is calculated as 37 and 16(1), which equals 5. This is the same result as 37% 16, but the bitwise operation is faster. This clever use of bitwise math is one reason why HashMap performs so well. HashMap relies on two key methods, hashcode and equals. If two objects are equal according to equals, they must have the same hashcode. This ensures that entries are placed in the correct bucket and can be found efficiently. If these methods aren't implemented correctly, HashMap's performance and correctness can suffer. The hashcode method generates an integer value for an object. This value is used by HashMap to determine the bucket index. While different objects can have the same hashcode, it's best if unique objects produce unique hashcodes. This reduces the chance of collisions and improves performance. The equals method checks if two objects are logically the same. In HashMap, this method is used to compare keys when searching for a value. If two keys are equal, their values are considered the same entry. Proper implementation of equals is essential for correct HashMap behavior. Every Java object inherits hash code and equals from the object class. However, for custom objects, it's important to override these methods to ensure they work as intended in a HashMap. This customization allows HashMap to store and retrieve your objects efficiently. To summarize, HashMap uses hashing to quickly locate buckets, handles collisions with separate chaining, and dynamically resizes to maintain performance. It relies on hash code and equals for correct key management. These features make HashMap a powerful tool for efficient data storage and retrieval in Java. Compared to lists and arrays, HashMap offers direct access to values without iteration, supports dynamic resizing, and allows for flexible key types. These advantages make it a go-to choice for many Java developers. However, it's important to remember that HashMap is not thread-safe by default. Java deliberately separates non-thread-safe and thread-safe collections. HashMap is not thread-safe, meaning it shouldn't be used in concurrent environments without proper synchronization. For thread-safe operations, Java provides alternatives like ConcurrentHashMap, which builds on HashMap's design. HashMap is ideal for scenarios where you need fast lookups, such as caching, indexing, and storing configuration settings. Its flexibility and efficiency make it suitable for a wide range of applications, from simple programs to complex systems. While HashMap is powerful, it has some limitations. It's not thread-safe, and performance can degrade if many collisions occur. Also, the order of entries is not guaranteed. For ordered maps, consider using linked HashMap or tree map. To get the most out of HashMap, always override hashcode and equals for custom key objects. Choose an appropriate initial capacity and load factor based on your use case, and remember to use thread-safe alternatives in concurrent environments. In real-world Java applications, HashMap is used everywhere, from storing user sessions to managing caches and implementing registries. Its speed and flexibility make it a favorite among developers. Understanding its internals helps you use it more effectively and avoid common pitfalls. The HashMap API provides methods like put, get, remove, and contains key. These methods make it easy to add, retrieve, and manage entries. Familiarity with the API allows you to leverage HashMap's full potential in your projects. Some common mistakes with HashMap include forgetting to override hashcode and equals, using mutable objects as keys, and not considering thread safety. Being aware of these pitfalls helps you write more robust code. HashMap manages memory efficiently by resizing buckets as needed. However, be mindful of memory usage when storing large numbers of entries. Choosing the right initial capacity can help avoid unnecessary resizing and memory overhead. In multi-threaded environments, HashMap can lead to data corruption if not properly synchronized. For safe concurrent access, use ConcurrentHashMap or other thread-safe collections provided by Java. Understanding this distinction is key for building reliable applications. Since its introduction in Java 1.2, HashMap has evolved with improvements like treeification in Java 8. These enhancements ensure that HashMap remains efficient and relevant for modern Java development. Staying updated with these changes helps you write better code. To wrap up, HashMap is a versatile and efficient data structure in Java. Its use of hashing, buckets, and collision resolution makes it ideal for fast data access. Remember to implement hashcode and equals properly, choose the right settings, and use thread-safe alternatives when needed. Mastering HashMap will greatly enhance your Java programming skills. With a solid understanding of HashMap, you're now ready to explore more advanced collections like ConcurrentHashMap. These thread-safe variants build on HashMap's foundation, adding features for safe concurrent access. Stay curious and keep learning as you deepen your Java expertise. Thanks for joining this deep dive into Java's HashMap. Understanding its inner workings empowers you to write more efficient, reliable, and maintainable code. Whether you're building simple tools or complex systems, HashMap is a valuable part of your Java toolkit. Happy coding!